today we are discussing Huffman's algorithm. Using Huffman's algorithm, we create a 2 tree which is called a Huffman's tree, and using Huffman's tree we can calculate minimum weighted path length. Before discussing Huffman's algorithm, first of all let us know something about a 2 tree. See, a 2 tree is a binary tree where every node either has no child or 2 children. So, this node is not having any child. So, this is 2 tree. See, the root is having only one child. So, this is not 2 tree. In this, the root is having 2 children, this has no child, this has no child. So, this is 2 tree. What about this? This is also 2 tree because 2 children, no child, no child and no child. So, this is also a 2 tree. So, after 2 tree, now first of all let us find something about weighted path length. What is weighted path length of a 2 tree? Weighted path length of a 2 tree. See, while calculating the weighted path length, we consider only the external nodes. That is why we have taken weights only in external nodes. So, if I have to calculate weighted path length, so this is the weight, first weight, and what is the path length? 1, 2. So, weight multiplied with path length will become weighted path length. So, 2 into 10, okay, because length is 2 and weight is 10. Now, what about this? Length is 1, 2 and weight is 5. So, 2 into 5. Now, what about this? Length is 1, 2, 3. So, path length is 3 and weight is 3. So, this. Now, what about this? Path length is 1, 2, 3 and weight is 2. So, 3 into 2. What about this? Path length is 2 and weight is 1. So, total weighted path length of this 2 tree is equal to 47. Okay. So, now we move to Huffman's algorithm. See, Huffman's algorithm uses a greedy approach, okay, and where we are using a bottom up technique. So, what happens? Let us consider that we are having W1, W2, W3 up to Wn n weights. Okay. So, if we are having n weights W1, W2 up to Wn. So, what do we do in Huffman's algorithm? We select 2 smallest entities, okay, and then we combine 2 smallest entities into a 2 tree. Okay. So, initially if there are n entities, so see first time what will happen? We will select 2 smallest, we will combine it into a 2 tree. So, now n minus 1 entities will be remaining. Now, second time what will happen? Out of those n minus 1 entities, now again we will be selecting 2 smallest, we will combine them into a 2 tree and now n minus 2 entities will be remaining. So, at last what will happen? At last we will come up with a single 2 tree which will be called Huffman's tree and which will be having minimum weighted path length. Okay. So, let us take an example. See, initially we are having 1, 2, 3, 4. Initially we are having 4 entities. So, what will we do? We select 2 smallest frequencies or 2 smallest weights. So, smallest weights are 1 and 3. So, we will be selecting 1 and 3. We will make a 2 tree out of 1 and 3. So, this is the 2 tree. 3 plus 1 is equal to 4. One side is 3 and one side is 1. Okay. Since this is not a binary search tree, this is because 2 trees are binary trees. So, we need not to follow the restriction that left should be smaller than parent and right should be greater than parent. So, C can be placed in left hand side also and right hand side also. So, what we have done? We have combined C and D into a 2 tree, okay, this 2 tree. So, now how many entities are there? Okay. So, now we have 3, 1, 2 and 3. So, next time we will consider these 3 entities and we will select 2 smallest weights. What are two smallest weights? One is 5 and other is 4. Okay. 4 and 5. So, now we will be combining 4 and 5. So, if we combine 4 and 5, so 9. Okay. One side is B 5 and okay. So, this B 5 is one side and other side of 9 is this entire thing. Okay. So, other side of 9 is this entire thing, because we have combined this and this. Okay. So, this becomes one entity now, and this is the second remaining entity. So, next time what we will do, we will combine these two. So, when we combine these two, so we come up with this 2 tree. Okay. So, what we have done, we have combined 9 and 10, because this is 9 and this is 10. So, after combining 9 and 10, we got 19. One side is A10 and other side is this entire 2 tree. Okay. So, this entire 2 tree is on other side. So, this is our final 2 tree, which will be called Huffman's 2 tree and which will be having minimum weighted path length. So, what is the minimum weighted path length of this 2 tree? This is 1 into 10, 1 into 10 plus 1, 2, 2 into 5, 2 into 5 plus 1, 2, 3, 3 into 3 plus 1, 2, 3. So, 3 into 1. So, this becomes the minimum weighted path length, which is 32. So, this is the minimum weighted path length for this Huffman's tree. Okay. So, now the second part, which is more interesting, is how do we generate Huffman's coding. So, Huffman's coding is used for data compression. It is used for data compression. It means using Huffman's coding, we can reduce number of bits representing the data. Okay. So, which will result in saving of space while storing data and saving of transmission time and bandwidth in data transmission. Okay. So, because what we are doing, we are reducing the number of bits of transmission. How will we do it? Let us see. And in Huffman's coding, we get a variable length code. It means every character does not get the same code length. Every character will have a variable length code. Okay. So, let us take an example. Suppose we want to transmit this text, or we want to save this text, we want to compress this text. Okay. So, this is the text. Now, A is appearing 20 times, B is appearing 12 times, C is appearing 6 times, D is appearing 5 times, E is appearing only once. Okay. Normally, what we do, because we have a character set of 128. So, earlier we were using a 7-bit ASCII code to represent it, but now we are taking standard is 8-bit ASCII code. So, using 8-bit ASCII code, using 8 bits we represent every character. So, A, B, C, D and E, so all of them will be represented using 8-bit ASCII code. If I remember, ASCII value for A is 97. So, then 97 will be changed into a stream of zeros and ones, okay, which will be 8-bit stream of zeros and ones. So, now what will be the total number of bits if we are using ASCII code, 8-bit ASCII code. So, because for every character we are using 8-bit ASCII code. So, total number of bits will be 352, because total number of characters are 44. So, 44 into 8 is equal to 352. So, now this is when we are using as 8-bit ASCII code. Now, since we are having, if we carefully see the text, so we are having only 5 characters in this text. Okay. So, now what happens if we design our own code for 5 characters? Okay. Suppose I have 2 characters, so using 1 bit I may represent them. Okay. 2 characters 0 or 1. Okay. Now, if I have 2 bits, then using 2 bits I can represent 4 characters. Now, if I have 5 characters, then I require 3 bits. Okay. So, see, for A, if we have a 3 bit code 000, for B 010, for C 011, for D 100 and for E 101. So, we have decided that these will be codes, 3 bit codes for A, B, C, D and E, because in this text we were only transmitting A, B, C, D and E. So, now what will be the total number of bits to be transmitted? Since there are 44 characters and every character is taking 3 bits. So, total number of bits will be 132, okay, which is quite less as compared to when we are using a standard 8 bit ASCII code. Okay, because if we are using 8 bit ASCII code, so number comes to be 352. Now, we have reduced it to 132. Now, let us make a Huffman's tree by considering the frequencies of characters in given text. See, A is appearing 20 times, B is appearing 12 times, C is appearing 6, D is appearing 5 times and E is appearing 1. So, what we will do? We will select the smallest 2 and we will combine them into a 2 tree. Okay. So, next time, see, first time there were 5 entities, now there are 1, 2, 3 and 4 entities. Out of these 4 entities, we will select the smallest 2. So, next time we will select 6 and 6. Now, we will combine them. So, we have combined them and these are 2 remaining entities. What will we do next time? Next time, we will again combine the smallest 2. So, this is 1 and this is second. So, we will combine them into a 2 tree. So, see, this was combined with this. So, this is the result. Okay. Now, we have only, after this we have only 2 entities, one is 20 and second one is 24. Now, we combine these 2 entities and this becomes our final 2 tree, which is called a Huffman's tree. Okay. So, now if we have to generate codes, so we will be generating like this. We start from root, left is 0, right is 1, left is 0, right is 1, left is 0, right is 1, left is 0, right is 1. So, what is code for A? 0. What is code for B? 1, 0. What is code for C? 1, 1, 1, 0. What is code for D? 1, 1, 1, 0. What is code for E? 1, 1, 1, 1. Okay. So, A is taking 1 bit and how many times A is appearing? 20 times. B is taking 2 bits and how many times it is appearing? 12 times. C is taking 3 bits and how many times is it appearing? 6 times. D is taking 4 bits and how many times it is appearing? D is appearing 5 times. E is taking 4 bits and how many times it is appearing? Only once. So, okay. So, if I add all this, then I get a number 86. Okay, because 20 plus 20 plus 24 is 44 plus 18 is 62 plus 20 is 82 plus 4 is 86. Okay. Now, same can be calculated using this path length. Okay. If we calculate minimum weighted path length of this 2 tree, okay. So, minimum weighted path length will be 1 into 20, 1, 2, 2 into 12, 1, 2, 3 into 6, 1, 2, 3, 4 into 5, 1, 2, 3, 4 into 1. We will add all of them. So, 1 into 20, 2 into 12, 3 into 6, 4 into 5, 4 into 1. If we add all of them, then we get minimum weighted path length, which also comes to be 86. Okay. Now, let us have a comparison. See, when we were using standard 8-bit ASCII codes, it means we were not compressing our data. So, what was the total number of bits required? 352. When we assigned our own code, 3-bit code, then what is the total number of bits? 132. And when we used Huffman's algorithm and generated Huffman's coding, then what is the total length? 86. So, we have saved good number of bits. So, what do we conclude? See, the character which is having the highest frequency is attached nearest to the root, and the character which is having the lowest frequency is at the bottom or is farthest from the root. So, in this way what we do? We reduce our total weighted path length. That is why we say that because we have generated a variable length code. Using Huffman's algorithm, you generate a variable length code. The character which was appearing more number of times has got single bit code. The character which was appearing maximum number of times has got single bit code. And the character which was appearing only once has got a 4-bit code.